All right, it is Monday morning. Oh, and February too. Happy February. Good to see you. Thanks for being here. Middle of chapter 18 still, we could say. There's a lot going on in this chapter. Electrophilic aromatic substitution. Now we're getting into the polysubstitutions. That's the tricky part. The di substituted, even tri, tetra. We can go up to hexa-substituted benzenes. And the directing groups, the directing effects of things is the important deal. Homework 3 will be due Wednesday. We will finish the chapter probably today, but we'll have plenty of time to review. Quiz 3 will be on Thursday night due. It's not posted yet. I'm still making it up, so look for it on Learning Suite soon, hopefully later today. Test 1 starts on Friday. It goes through Monday. So you have Friday, Saturday, and Monday. And all the COVID protocols are handled over there. Things have been going well. I've talked to some people who've had tests over there recently. It should be fine. Distancing and disinfecting things. The hours, check the hours always to be sure about that, especially if you're waiting till Monday night to do it. Monday, there is a late fee, I think starting in the afternoon sometime, so be aware of that. Sample test 1 is already on Learning Suite. It's an old test that we gave for the same section. There's a key for it as well, and on that key, the sample test 1 key, there's also the answers to the worksheet problems, those harder problems. Some people were asking me about those in recitation, and I don't think I told you where to find the answers to those, but work them without looking at the answers. That's always the good thing. Questions on any of this stuff coming up? Anything there business-wise? Okay, Braden, let's look up here first at the general chart. Electrophilic aromatic substitution where we've already got a functional group on benzene. So is that functional group an electron donor? Can it stabilize a plus charge right next to it? Or is it a withdrawing group with a partial or a full positive charge right next to the benzene? That will deactivate, slow down the second addition, and give the meta product. And I like these static electropotential energy diagrams here. This one is for aniline, I think. Yep. You see the lone pair on the aniline donating into the benzene ring. The redder orange color is higher electron density. So you see the pi electrons, very red. Here's benzene. They're red also. We can do all these substitutions on benzene itself. And that's the rate normalized for benzene, where H is the functional group, right? And it's, got high electron density, 6 pi electrons. Reddish. But look at this. Here's the computer simulation for nitrobenzene, NO2. Look at that. You see the full blue thing there? That's that plus charge nitrogen. It's always plus charge, right? And what does that plus charge right on the ring do to the electron density on benzene? It goes down. It's greenish now. Greenish blue color is low electron density, okay? High electron density is the redder color. So you can see by the shading there what we're talking about. Relative rates, whether it's faster relative to benzene or slower. And then the directing effect. Anything that's donating electron density will give orthopara products. Anything that's electron deactivating will give meta products to avoid placing that plus charge next to that position. Now we went through this last time. We all got writer's cramp, me with the chalk and you with your pen trying to keep up with me to go through all the resonance structures of each of the 3 pathways here. But you need to do that a couple times to lock in the idea, what we're talking about here. Here's toluene. We're putting on a new electrophile. If we put it on ortho, the plus charge can be here, resonance over here, or resonance right there. And this is the important one, shaded here. Why? Because that's tertiary position. That can benefit from the electron donating effect of the methyl group. Okay, and then loss of the proton, you got to finish the mechanism. The last step is with base, of course, give the ortho product. That's favored one. Isoelectronic with it is down here, the para attack. If you put the electrophile down there, you have plus charge here, here, there's the good one, and then over there. So 2 secondaries and a tertiary carbocation, we could say. is better than the meta attack. If we put the electrophile there at the meta position, the 3 position over, then we have the plus charges here, here, and here. Notice they're all secondary, okay? So it's not as favorable going that pathway. So we get this selectivity issue coming out here, ortho and para. And here's aniline, and I think we did phenol. We'll start with phenol, we'll review that. We got lone pairs on aniline and on phenol. So you see if you put the electrophile on there, ortho, secondary, tertiary, and there you get that extra resonance effect right there. Now it turns out with aniline, there's only one electrophilic substitution reaction that works reliably, and that's bromination, okay? No Friedel-Crafts on aniline and no acidic conditions. So that rules out nitration and sulfonation. Those are both poor. In fact, if it goes at all, they'll give meta products very slowly. And that's because anilines are basic. We'll have to review that at the board. You'll see there's significant problems with aniline. Okay, that doesn't hold with phenol. Oxygen's a lot less basic than nitrogen. But you see here, comparing to the meta, then we got secondary, secondary, secondary. So that's not as favored here. And really, this is limited to bromination. Okay. Those of you who read ahead know that there are some caveats, some exceptions to the rule here. Then para attack, you get that same tertiary carbocation with the extra iminium ion cation, just like there and there. Okay, and then we did, instead of nitrobenzene, we compared the strong deactivating group. Which one did we do? We did trifluoromethyl, remember? And that was the strong meta director. Slow, much slower rates. All these principles apply here with nitrobenzene. In fact, nitrobenzene is the most deactivated. Can't do Friedel-Crafts here. It's just too deactivated. Friedel-Crafts electrophiles are not as potent electrophiles as nitration, sulfonation. So no Friedel-Crafts with nitro. In fact, we're going to say no Friedel-Crafts reaction with any deactivating group. Okay, and I'll summarize those exceptions to the rule here. But you know, with nitro, you can do all the other 3 reactions, right? You can do bromination. You can do nitration, sulfonation. Okay, those electrophiles are potent enough, but no Friedel-Crafts with the nitro. But if you put on the second electrophile, if you examine the ortho pathway here across the top, look, you end up with that plus charge right next to the plus charge there. Okay, by Coulomb's law, that's a no-no. 2 similar charges next to each other, that's highly repulsive. Okay, that's like having 2 empty orbitals right next to each other. That's just very high in energy. So the ortho pathway is deactivated. Meta pathway is okay because you never put the plus charge, you see, right next to the nitro. You've got to examine, though, the resonance structures. You've got to go through that and push the electrons to convince yourself. Rely on first principles, okay? Don't just memorize rules, you know. That's okay. You'll get a feel for it. You know, what's electron donating, what's electron withdrawing, and then just memorize, yeah, ortho-para for the donors, yeah, meta for the withdrawers, but rely on the resonance structures. Go to the mechanism here. So yeah, that avoids it. So it'll do that second substitution here, meta position. Para, same thing. It puts the plus charge right there on that. Okay, yeah, I'll do that later. All right, let's go to the board here, Braden, and go through some of these examples. We did phenol last time, I think. And, you know, the key here with phenol was if you put on the electrophile here and go to the intermediate, you see, you can see your first resonance structure going the ortho pathway. Look, you've got the plus charge right there. So you don't really need to examine all the others. You could have the plus charge here, here, here. They always alternate, right? They're allylic cations, so they go around. But the thing with phenol and aniline, you've got the extra one here. So the ortho and para products are definitely the main ones with phenol. And it's very fast with phenol. That lone pair, that resonance effect is the dominant effect. Even though superimposed on it, you have the electron withdrawing inductive effect. It's an inductive withdrawing group because it's more electronegative through the sigma bond to that carbon. However, those two lone pairs are available to come into the ring, okay? And that's this effect to give you that extra resonance. So the key thing here is resonance, again, with that donor group. Now, phenol is not nearly as basic as amines, okay? So an aniline is an amine. The lone pair, it's a nitrogen. It's less electronegative than oxygen. That's why oxygen, alcohols, water are not nearly as basic as amines. It's because they hold on to those electrons better. The pKa of hydronium ion is what? -2. The pKa of protonated phenol is even lower, okay? Because these lone pairs are in resonance with the benzene ring. Makes them less available to be a base. But the nitrogen is 2.8 on the Pauling scale instead of 3.6, right? So it's not holding on to those electrons to the same degree. It's an even better donor into the ring. However, it becomes basic. You can protonate it, and that's the problem with the basic conditions, okay? And the Lewis acids, when we talk about Friedel-Crafts with aniline. The only one that works reliably with simple anilines or amines, we can have alkyl groups here in place of these hydrogens as well, okay? We could have 2 methyl groups here instead of the 2 hydrogens. It still function like an aniline, okay? And with bromination, it's very fast reaction. And in fact, it gives polybromination. It will hit every ortho and parasite available. There you go, the parasite. I avoided saying that last lecture. We're not talking about entomology or infections here, but the paraposition, there you go. I'll try to control myself. Okay, no jokes about parasites during this chapter. But it will give overbromination, this lone pair. You can see how it goes. And we have the active Lewis acid, right? In fact, aniline and phenols are so active, you can get monobromination just with bromine itself. Now remember, we started the chapter telling you if you react benzene with bromine, no reaction, right? I lied, I guess. If you react phenol or aniline with bromine alone, without the Lewis acid, you can get the mono to go fine. And why is that? Because it's such a strong donor now, right? So this can react with bromine on its own, right? Because you got the lone pair there. And it's just the ortho or the pair product, and you control that with mono. The stoichiometry is tough to control here, even if you try to limit it to one reagent. Usually your major product will be the tri in this case, okay? So you can adjust that if you use excess here. If you want to hit every site, that's okay. But if you want to just do mono, either with phenol or with aniline, then just use the one equivalent without Lewis acid. So without the Lewis acid, you get mono. Okay. Questions on that? That's a little bit tricky, but it relates to that lone pair issue, whether it's on there. Now, the other issue, this lone pair, right? This is strong acidic conditions, right? And what does that mean? If you react a strong acid with a good base, what happens? It gets protonated. The pKa here is actually 5. That's a weak acid itself, but that means it easily got protonated by this strong acid condition. Now you have a plus charge right on the benzene, right? So it's going to go meta, if at all, but it's strongly deactivated now. So it's not a good reaction, okay? It gives a mixture of meta and para products, but in low yield and very slow. It's not productive. We don't do it that way. If you want to do the other reactions, including Friedel-Crafts, you need to put on the acetate group. You need to form the amide. And we'll show you how to do that in the future. But all of these here, you can do Friedel-Crafts, you can do bromination. You've got to use the Lewis acid now, though. And this lone pair now is in resonance here, but it's still here available to go into the ring. So you can do nitration, okay? You can do sulfonation, okay? So all the reactions are available. There's 2 Friedel-Crafts, right? Alkylation and acylation. If you have the amide, you attenuate, you see, the basicity here. because it's in resonance here, it's not nearly as basic. If you protonate an aniline, that pK is about 25. Much, much weaker acid, okay? That means much less basic, right? This is a stronger base, okay? Under acidic conditions, you can easily protonate it, and then meta-director or just too super slow, okay? The way around it is to start with the aniline. We'll show you how to do that reaction later. You might see it. Maybe I showed you. Yeah, the sulfa drugs. I showed you the synthesis of sulfa drugs. We had an aniline there. Okay, but yeah, here if you've got it there. And that's a separate type of deal. Questions on that? The phenol, the aniline, the amide. Kind of a complicating factor. All right, let's look at carbonyls. It's a lot of carbonyl compounds. We've got aromatic here. There's something here. Now that's different, right? Here we've got resonance structure like this, where we've got plus charge right on the benzene ring, right? For that important resonance structure. So what are these going to be? These are going to be deactivating, and they're going to be meta-directors, okay? Let's look at the data here for benzaldehyde. So if we take benzaldehyde, treat with nitric acid, sulfuric acid, what are we going to get? We're going to get the meta product. And it's an 85% yield. And so I'm jumping right ahead to the product. Now can we use the mechanism to rationalize that? So we want to put on our electrophile at the meta position, because then we'll have plus charge here, here, and here. We'll avoid placing it at the ipso position, it's called, on the same carbon bearing the functional group. Yeah, I should avoid using too many terms, but that's called the ipso carbon, sorry, mechanistically. But what's the true electrophile for nitration again? We need to review that. Hopefully that's on the tip of your tongue now. What is the true electrophile for nitration? NO2 plus, very good. So that's what we're looking at mechanistically, right? Nitronium cation. Let's go ahead and put it on there. So what will our mechanism look like? Plus charge there, nitro, carbonyl, other stuff there. So what's our other resonance structure? Right there, okay, and right there. Notice it's never right there. Well, let's compare it. You know, why no para? Let's do para, okay. And what would that look like? Like this. Nitro there, and plus there. See, the para pathway would give us resonance structure right there. And that would have the positive charges again together, which is going to slow that pathway down. So ortho para positions are deactivated to a greater degree than the meta position. Electron deactivating groups deactivate the entire benzene ring, all the positions, but it selectively deactivates ortho and para to a greater degree than the meta pathway, because the meta allocation avoids placement, here it is, at that position, right? Here, here, and here. Whereas ortho or para, they're isoelectronic. You should recognize that now. Plus charge here, here, and here, okay? So that one's going to be slower. And this one, finishing off the mechanism, make sure you remember that. What do we say? Either water or bisulfate, whatever, gives us then the product. Okay, questions on that? So all of those withdrawing groups, anything that has a carbonyl conjugated, cyanide as well. If you have a triple bond here to nitrogen, that same thing. You have this partially positive cyano group. If you have a sulfonic acid on the benzene ring already, that's what? You've got partial positive charge on the sulfur. Okay, so these are deactivating groups also. And by far the best deactivator, like we just showed there on the board, is this one. The nitro, the NO2 group, always has a plus charge. It's got two resonance structures, but notice both of them have the plus charge here. So it's strongly deactivating. All of these are what? Meta directors. You should be able to push the electrons and verify that. All right, let's look at some data here for another example. And it's one we kind of showed, I think, when we were doing nomenclature. But I like the data for this synthesis because it shows you what's going on here. So here we have toluene, nitric acid, sulfuric acid. What's the product? So second level of understanding, reactivity, right? Reagents, starting materials. Can you analyze that substrate and tell whether it's a donor group? Is it going to be ortho para directing, or is it going to be a withdrawing group meta directing? What do you say? Ortho para, yeah. In fact, it's going to give a mixture. It's going to give the ortho, like we said, plus the para. It gives a trace amount of the meta. You can ignore that though. For synthesis, you need to separate these two and use them individually. If you're from, that's fine. This one has a higher melting point, for example. You can crystallize that away. But let's do a second one here. Let's react it with more nitric acid, more sulfuric acid. We've got to increase the temperature to 100 degrees. First one we could do at room temperature. Now, why do we have to heat up the reaction now? We're using, what, nitrotoluene products, right? Take the mixture on or individually, it doesn't matter. We're doing a second nitration, right? We're getting a tri-substitute benzene. So what's up with this higher temperature? Why do we need that? Anybody? Yeah. Yeah, this nitro group has a plus charge right on there, so it's deactivating all the electrons out of the benzene ring and making it less nucleophilic. We still have a nitronium cation, and it's going to give this product. It's going to give dinitrotoluene. Okay, you can get a good yield of that. Okay, now you can kind of see where we're going here, right? Let's do it again. Nitric acid, sulfuric acid. If I can draw this morning, H2S, just going again. And now we very carefully have to heat it up to 160 degrees. So higher still, right? Because we have two nitros on here. Okay, so what's the product? Trinitrotoluene. And what's the acronym in common usage? TNT. Okay, the explosive reagent. It's a solid material. It's got a yellow color. You can mix it with diatomaceous earth, put it in a tube, whatever, or nitroglycerin. You can nitrate other things, including alcohols. You can take glycerin, which is a trial, and make the trinitroglycerin. That's highly unstable because it's a liquid. They're thermodynamically unstable because they can give off a lot of gaseous molecules very quickly. So yeah, TNT, trinitrotoluene, more specifically, it's what? 2, 4, 6 trinitrotoluene. So the higher temperature to make it there. And if you apply a shock or an electric spark to it, you can make NO, NO2, CO, and CO2 very quickly. And this is a hallmark of organic compounds where you have a lot of heteroatoms within the molecule. They become thermodynamically unstable. You can easily form these other compounds. It's kinetically stable. You can make it and it won't explode on its own. It's mainly used for the mining industry and road making, where you need to remove a lot of earth. But you can see it's not actually a combustion reaction. We're not combining it with oxygen and burning it. We're applying a shock here, and it can easily reform to all these molecules. And these are all gases, right? So go from a solid to a bunch of gases. That's the understanding there. Anyway, questions on that, the reactions? Yeah. Yeah, you're a very high temperature. You got to handle it very carefully. Okay. Don't do this, okay? All these materials are very, very, very dangerous that way. So yeah, that's about all I should say about that. Okay. Let's get into some other dye substitute reactions. So how about this one, where we've got 2 on here. Oh no, I need to do this one first. Chloro or bromo, or any halogen for that matter. Now, inductively through the sigma bond, they are deactivating, okay? And they're usually more electronegative than the other groups we talked about. So they tend to deactivate the benzene and give a slower reaction here for all of the reactions. However, they're still orthopara directors. They're the only ones that's actually kinetically deactivating slower reactions, and yet they still give orthopara products. And that's because you can see, if you do the mechanism, you'll put the plus charge right on the halide. Okay. Well, what else is there? Lone pairs, right? So they can still, by resonance, donate into the ring, but inductively they're more deactivating than others. So you've got kind of a mix there on those. In fact, let me summarize all of the exceptions here, we can say, to the rule, and we'll have these up here. Let's see. Halogen with phenol and aniline, we get mono, okay? But with the Lewis acid, we get poly, okay? So that's kind of one thing to keep track of. No Friedel-Crafts with deactivating electron withdrawing groups, okay? Halogens are okay for Friedel-Crafts, but all of the other deactivating groups, no there. We'll point that out. The worst is aniline, where you can actually form a complex with the Lewis acid for Friedel-Crafts. The aluminum will actually grab the lone pair. Well, I'll give a plus charge right on there. So no Friedel-Crafts with aniline and any other deactivating group. But it's okay with the amide. Okay, there's there's the other corollary to that, I guess. Friedel-Crafts alkylation often gives poly. And that's because when you put one alkyl group on the benzene, that's a donor now. So oftentimes we get di, tri, even tetra methyl benzene instead of just selectively one. That can be difficult to control, so it's something to keep an eye on there. If you have aniline here with any strong acid, so the strong acids, of course, nitration and sulfonation, right? And both of those, no, because again, you're protonating the lone pair on the nitrogen, okay? Yeah, and the other one is what? How? Sorry to get too many exceptions up here. Halides, okay, are slower, but they're still orthopara. I think that's all the exceptions. They're kind of scattered throughout the chapter, and I've already mentioned a couple of them already. But there, it's good to have them all in one place, I think. Yeah, question. Yeah, so right here, so if you have an aniline and you treat it with nitric acid, sulfuric acid, or sulfuric acid tritone sulfonylation, you're going to protonate this, right? And that will give you the protonated amine, and then what? It's a positive charge right on the benzene. So be very slow, the reaction. If you get any at all, it'll be a lot of meta product, okay? So it's not a good thing. But you can get around that and do all the other reactions if you make the amide, if you have the amide version of the aniline. Okay. Yeah, so keep those in mind. Let's Let's get into some polysubstitution now. Let's take metaxylene and let's nitrate it. So we got xylene. Remember that word starts with an X. They're 1,3 to each other. So they're both ortho-para directors. So this one's directing here, this one over here, this one here, and this one over here. This one's also over here. So notice you got a lot of positions here which are really the same, right? These two here are the same due to the symmetry of the molecule. This one in the middle is sterically kind of hindered being in between two alkyl groups. So these two over here, we do mononitration, okay, which is what we're doing here. And the main product is this, where the two groups on the benzene ring are enforcing each other, okay? They're both directing to that spot. So that one gives a good yield for that. And yeah, we don't need to worry about it too much. Let's see another one where they're enforcing each other. How about if we have the paranitrotoluene and we want to brominate? So where are we going to go here? Well, the nitro group's directing to the meta position, and notice the methyl's also directing to that position. So even though they're different groups, one's a donor, one's a withdrawer, they're both enforcing again. So there's only one product here, and it's the one right there. Okay. What? Be the same, right? either side. Just flip it around. All right, let's do a couple more like this, where we've got some choices to make. How about if we have paraxylene and we do Friedel-Crafts? Friedel-Crafts acylation. Now notice this one's directing here, but that one's directing there. They're not enforcing each other. If we go here, notice that's meta to that one. But there's symmetry in this molecule, right? All four of those spots are actually the same. So we don't need to worry here. Just put the acetyl group on any one of those, and they're all the same. And that's okay. All right. Both of those are activating the benzene ring. We put it on one position. They're really all the same. And there's an example where they're both donors, but they're not reinforcing the same position. Okay, but that's the only product you can get. Yeah. No, those are electron donating, so it's a fast reaction. Yeah. Okay, how about this one? We've got an aniline here. Well, actually, it's an N-methyl aniline with a chloride here. And we can brominate with just a molecule of bromine without the Lewis acid. We're going to get mono bromination. But notice this, right, is enforcing this position. Okay, it is an ortho-para director. What's this, though? This is also ortho-para director. Now we get to a point where we've got a conflict. Which one is the stronger donor, the stronger activator? And that's the case. When you have two resonance donors in conflict, which one do you go with? What do you think? What's the stronger one? Yeah. Yeah, so that'd be the aniline. Okay. So the anilines and phenols are the top electron donors by resonance. So you always go with those. So let's see. If we do that, we get this product. We get the bromo here, the chloro here, and the methyl aniline's fine there. Okay. But the stronger one is the aniline. Okay. All right, how about this one? Terbutyl and nitro. And we're going to brominate it. Which one are we going to go with? Let's see. An alkyl group is ortho, and para. So it's going to activate those positions. The nitro is going to favor this position, right, to avoid putting the plus charge on there. So here we have a strong donor and a strong withdrawing group in conflict with each other. What does the book say to do there? This is electrophilic aromatic substitution, after all. So the donor, the one that's making the electron richness in the ring more prominent, is the one that's going to direct the reaction. But now we have tert-butyl. And this position in between the two sterically may not be as favored. Let's see. What do you say? This ortho position is right next to the large tert-butyl. So actually you get more at the para position. Okay. So the major product is this. So again, we're going with the donor. And there's kind of a steric issue there. There's also some of this product here. But you can see with the big tert-butyl, if you put it down here, you avoid any clashes sterically in 3D space with that. Okay, questions on that so far? Okay, let's do some synthesis problems. So here we're going to do it the other way around, right? We're going to have a target in mind, and we're going to start with benzene and then do the reactions to get to the product. But we're going to have to do it in the right order, right, to figure out how to get there. So let's see. How do we make this? Meta-bromo acetophenone, starting with benzene. Well, obviously we're going to have to brominate it at some point, acylate it, do Friedel-Crafts acylation. But in what order? Let's analyze the relationship here. We want meta for the product. Now analyze the groups. Let's see, a ketone here, yeah, is a meta director. Okay. What is a halogen? Halogen's ortho and para director. So which one should we put on first in order to get the disubstitute product selectively? Put the ketone on first. So do the Friedel-Crafts acylation first. You'll see some consequences here, right? If we did bromination first, followed by acylation, we'd get the ortho para products, right? Because that's how it's directing that second substitution. But here we can get the acetophenone, and then what? Then brominate. We have to have the Lewis acid in there. And yeah, that two-step procedure will give a nice yield for that desired meta product. Okay, what if we wanted the para? You see, we'd have to switch the order. And by simply switching the order, look, we get the selective process here. And, you know, the key here is to kind of draw out the intermediates and think about each one. You know these 5 reactions now, okay? So it's manipulating those reactions and then analyzing the directing effects that are going to help you out here. But no, this is the same reactions, right? A different structural isomer outcome, okay? Different constitutional isomers depending on the pathway we took, either acylation first or bromination first. Okay, how about this one? Benzene, and we want to go to this. Ethyl, chloroethyl benzene, para to each other. Which one can we put on first? Well, notice they're both para directors, right? Ortho-para directors. So it doesn't really matter in this case. Getting on the Friedel-Crafts alkylation thing is usually a good thing, although we warned you, over alkylation can occur sometimes. Sometimes it's better to put on a more deactivating group than the alkyl group first. But if you do this carefully and get your ethyl on there first, and then chlorinate, you'll be fine. So here, it really doesn't matter, the order. We could have chlorinated first, and then we could have alkylated first. So the order doesn't always matter if they're reinforcing each other. That can be okay. All right. What if we wanted the meta one of this? So meta chloroethylbenzene. Now we got a problem, right? We can't form ortho products. We want this, meta. Notice, this is ortho para director. This is ortho para director. Look at that. Neither is meta enforcing. But do we know how to make that group from something else? What's going to be our intermediate here, and what type of reaction are we going to do? We're going to go to this intermediate. When we think about the retrosynthesis now, why am I proposing that for our retrosynthesis? Because this ketone is now what? A meta-director. Okay. So this is the key. Once you understand these reactions and have a couple in mind. So what can we do here to give this? We can do zinc, mercury, HCl, or we can do what, the Clemenson. I'm sorry, that one's the Clemenson, and this one's the Wolff-Kishner. Either one of those reduction reactions will take that ketone down to the alkyl. Okay. Remember, I said you don't need to know the mechanism. It'll put those two groups on there. So how do we get this? So now we got to analyze that one, right? This is our meta director here. Okay. So what do we want to put on first? We want to have that acetophenone on there, right? And then we want to chlorinate. Okay. You see? Because that will be another director. If we chlorinated first and then did Friedel-Crafts, we get the para product. Okay. So we don't want to do that. So it's actually a three-step thing from benzene, right? Friedel-Crafts acylation, then chlorination, then reduction. So you see the challenge of these reactions. These things begin to get a little more difficult. You got to analyze them from both directions. The reactions how they enforce each other, and which group you can put on first. All right, how about this one? Let's make PABA, para-amino benzoic acid. We saw this as a UV blocker. It's also the endogenous ligand in bacteria to make folate. So we saw it in a couple different things in the name, para-aminobenzoic acid. How are we going to do it? Well, how do we make anilines, and how do we make carboxylic acids? These are two different things. And this kind of points up some reactions we need to know here. Let's see, we can take a nitro group. We know how to put those on. And we have our carboxylic acid already on there. And to take a nitro down to an aniline, we can use H hydrogen and palladium, or we can use HCl and zinc and tin metal, SN, stanium, okay, for tin. These are two different new reduction reactions, right? So a nitro group with two oxygens, taking off those oxygens, putting on hydrogens, those are reduction reactions, right? These conditions don't bother the carboxylic acid. Okay? So this gets us into a functional group we know how to put on now. So this is one of these extra reactions, okay? Kind of like the Clemenson, the Wolff-Kishner, this reduction of nitro to aniline there can help us make that product. Okay, how do we make this guy here? Well, this is another peripheral reaction or corollary reaction. We can take nitrotoluene and oxidize the alkyl group, okay? And there's a couple ways to do that. With chromic acid, that's chromium now in there. That's not sulfuric acid. That's a redox active transition metal. So you can make chromic acid here from the chromate salt. I'll show you dichromate and H2SO4. Or you can use permanganate, KMnO4. These are oxidizing conditions, right? So this is another type of reaction. By the way, you don't need to know the mechanism of this one either, or this one. I can tell you a little bit about the mechanism. You have to have at least one benzylic hydrogen atom there. So tert-butylbenzene will not do this allylic oxidation. But if you have an ethyl group or an isopropyl or any other type of alkyl group on the benzene, you can easily oxidize it, break carbon-carbon bonds, and put a carboxylic acid conjugated to the benzene in high yield. The easiest one to envision is just the methyl there, okay? So we've got two groups we know how to deal with now, right? Now we've got toluene, and we can just nitrate that, right? So treat toluene with nitric acid, sulfuric acid. We get para-nitrotoluene. Oxidized with chromic acid or KMnO4, we get the carboxylic acid. Then we can reduce down the nitro to the PABA product, okay? So we don't know how to put these on yet, okay? We put this on indirectly and that on indirectly using these other reactions here. Questions on that? No mechanism on those, but it ties in with what you've got there. You've got the benzene and then the two groups para to each other and get into that. Questions on that? Yeah, please.
What were the reagents for the
Chromic acid, this is sodium chromate. This is a salt. This is a little easier to deal with. This is very corrosive and toxic once you make it. So it's better to make it in the same flask in situ, we say. So you treat the chromate salt with the acid, sulfuric acid. That makes chromic acid in the solution. It's a red, deep red solution. And it will oxidize any alkyl benzene except tert-butyl from the alkyl benzene to the benzoic acid. Okay. And yeah, the nitro group, is already oxidized there. And then these reduction conditions, either hydrogen or palladium, hydrogen with palladium, or HCl10 reduces the nitro to the amino. Okay, SN stands for stanium. It's a Latin term. That's tin. Okay. Stannous chloride, what you brush your teeth with, right? Tin. Okay, SN. It's a metal. Questions on that? I think we'll leave it there. We'll cover benzylic radical halogenation next time, and we eliminated the benzyl chloride. I think I showed you how that works. You can put a bromo group at the benzylic position of an alkyl benzene under radical condition. We can eliminate that to make styrenes. Yeah, I showed you the synthesis of styrene. Yeah, that was in the class a little bit ago. We'll review that, and we'll do a bunch of other synthesis problems. And like I said, we'll be finishing Chapter 18 on Wednesday. So make sure you're up through that material very good. And then we got a couple things coming up, homework and the quiz. So we should be okay for the test. So very good. We'll see you next time. Thanks.